Good morning and welcome to a brief introductory video to Automated Video Analysis for Dynamic Systems, or AVADS. AVADS is a MATLAB user interface for processing kinematics through two-dimensional video data. These 5 files here can be downloaded directly from our GitHub page, github.com/GranadaLab. And as long as the avads.m and .fig file are stored in the same location, you can simply open the .m file and click Run to launch the AVADS user interface. We'll start with opening a new video. These 5 video files here can be downloaded through hyperlinks in our user manual and tutorial guide, and they show you examples of how to use AVADS to analyze classic physics or dynamics problems such as a pendulum, and to analyze human movement biomechanics data. So for this example, we're going to open treadmill running. This video is rather large, so it might take a minute or two to load. Alright, so here we have a participant running at their preferred speed on a treadmill. And we could just go through and watch the video if we want, but let's get right into the tracking. So the first thing we need to do is name the markers we want to track. Thigh 1, 2, shank 1, shank 2. So in this tutorial we're just going to track these 2 dots on the thigh and 2 dots on the shank, and we're going to use these to extract some information about knee kinematics during running for this participant. The first thing we need to do is set a threshold, which is going to set pixels darker than that threshold to black and pixels lighter than that threshold to white. What we want to do is segment out our markers against their background. So here at around a threshold of 90, we see our dark markers are now black and their light background is now white. That will allow us to automatically track them throughout the video. However, we do need the objects we want to track to be white, so in this case we need to invert our black and white image so that we're now tracking these white blobs. We're next going to manually digitize each marker we want to track. So we'll zoom in and digitize these 2 black dots, double click to zoom back out. Alright, and now AVADS puts a colored marker over the location that we clicked and over the markers as it's automatically tracking, just to ensure that you're tracking properly. And that's a little small, so let's increase the size of that marker, which just allows us to see it a little bit better. And the colors of these markers do correspond to the colors next to where we named each marker. So we're all set up to enable automatic tracking. And for this example, let's go ahead and just plot every 5 frames. So what AVADS is doing is it's tracking the location of each marker on every single frame, but it's only going to plot every 5 frames, which just speeds up automatic tracking. In this video, I am recording on a rather old laptop and also running some screen recording software, so it's going to go a little bit slower than expected. So AVADS is automatically tracking each marker in this video, and how it does that is it uses the position and location of the marker on frame I to predict where that marker is going to be on frame I+1. It then identifies the closest actually segmented object, or the geometric center of segmented objects, which are just white blobs in that threshold image as we saw before. It does that for every frame of the video, except for the first frame where we started automatic tracking on frame 2. On frame 1, we only had the position of each marker. We didn't have the velocity yet. So the first frame that we started tracking, we had to assume that the velocity of every marker was 0. So tracking does get better as tracking goes on. So for now, let's go ahead and stop the automatic tracking. Again, there's minor playback issues because I am redlining my laptop, but we can see that the markers are actually tracking appropriately, and we can go back and play through the video if we want to ensure that. So we'll just go back to the first frame here. You can play a little bit. And you can go through and play through the whole video if you wanted to, but let's go ahead and plot the position of the markers. So let's plot the position of marker 1. And here we have a plot of the continuous two-dimensional trajectory of the horizontal and vertical location of marker 1. And we can plot any of the markers that we just tracked. And right now it's giving us the location in pixel coordinates, but if we wanted an actual physical measurement unit, we can actually calibrate this video by measuring an object of known length in the field of view, entering the length of that object in pixels here, and its physical length in meters here, and click calibrate to calibrate the video, and that would give us the coordinates in meters. There's no marker occlusion in this video, where a marker is blocked for a period of time, but if there was, we could apply a spline or linear interpolation across the period of time where the marker was occluded to estimate its location. And we could also apply a low-pass fourth-order Butterworth filter with a user-defined cutoff frequency if we wanted to smooth our data as well. In this tutorial, we're just going to create a two-dimensional knee angle with a line connecting the first two markers as the thigh angle and a line connecting the third and fourth marker as the shank orientation, and the angle between those two lines as the knee angle. So let's go ahead and create that knee angle here. The first line again is markers 1 and 2. Second line is markers 3 and marker 4. And let's go ahead and just plot that knee angle here. So in the beginning of the video, the participant was going into knee extension. They contact the ground around here, and then they have some stance phase knee flexion, and then they go into extension again around toe off, and flexion during mid stance. So let's use AVADS to calculate peak knee flexion during stance phase. We could just read that rate off of the plot if we wanted to. But let's go ahead and use the calculating functionality over here. There we go. So let's say that knee flex or initial contact happens around frame 17, and that toe off happens, I think it froze again. Excellent. Let's say toe off happened around frame 51. And knee flexion is negative here, so we're going to look for the minimum position. We could look at the velocity or acceleration, which is just the first and second time derivative of these time series. And we said the knee angle was angle 1. So let's hit compute, and our result is 37.8. So if we wanted to save that peak knee flexion angle, type that in over here. And now it's going to export with our data when we save. So let's do that now. If we go back to MATLAB, there is now a new file in the same folder that we opened our video called treadmill running _processed. And if we open that file, we can see the variable that we just exported, all of our time series data, and the two-dimensional angle that we created. So if we plot the knee ang, we see that time series again, and we can do more analysis if we wanted to. So again, this is just a basic introductory video for users who want to really learn this program. We suggest that you look at our user manual and our guided tutorials, which will show you how to calculate a variety of kinematic outcomes from a couple different videos.